All right, guys. Before we start, do you have any questions? So hopefully by now everybody has their simulation running and you know how to visualize the data at least. If you still have trouble, just email me. We'll set up a Zoom session separately. Okay, so let's continue talking about trim, and today we'll finish with it. Let me see, is enough? Okay, all right. This is the scenario we were talking about where we have our hull, we have a certain weight that is initially at a given position, and then we move it forward to a new position. And then we said, all right, the combined center of gravity will be at a new location G1, and we know how to compute that. Once we compute this new center of gravity, we can, well, the distance between G0 and G1, we computed here. And once we know that, we can relate that to the trim angle, the angle by which the nose would either go up or down. Okay, and that's where we stopped. Tangent of theta would be this much. So we can relate this angle to change in the trim height, trim length. Okay, so where was it? Here. Okay, so this is from a previous lecture. We related theta to the trim, right? We said tan theta would be equal to little t over capital L. And now we have another expression for tan theta. Tan theta is this much. So we'll just equate the two things. We also know tan theta is little t over L. And this we derived previously. Okay, so we'll just equate the two, and we get T over L is W times H over delta 0 times GM longitudinal. Now, if we think about when we move this weight, we have changed the moment by a certain value. By how much? So we know what the force is. That's W. That's the weight. And we know the moment arm is G0, G1. So that's basically the change in moment, weight, the force times distance. So we have total change in moment is the force, which is weight times h, which is the distance moved. With these two things, we can figure out what our MCT is, meaning what is the moment required to change the trim by 1 meter. So MCT is moment required to change trim by exactly 1 meter. And in this case, if our change in moment is WH and our change in trim is little t, we divide it to get for a unit t what would be the required moment. Okay, so for t meters we require W times h. For 1 meter, we would require this much. W times h over little t, we can get from here. So this comes out to be delta 0 times GML over little l. So this is MCT. So that's a very easy way of computing the moment required to change your trim by 1 meter. Remember, for small boats, 1 meter is a huge trim value. But for, let's say, an aircraft carrier, it would not be that unusual. So let's do a few examples to see how we use this to determine the trim angle. So we're told that we have a ship of mass. And be careful when you work with units for mass or weight. You'll see it mentioned in tons, in kilograms, in Newton, kilonewton. So all of these, just be careful with what the units are. So here we're given it's 5,000 ton, 98 meters long, and it floats at draft. Now remember, since we are talking about trim, the draft is not equal throughout the ship. The nose draft, the fore draft and the aft draft might be different values. So we are given 5.5 meter forward and 6.2 meters aft. That's the two draft values. This ship is nose up or nose down? What condition is it in right now? In this particular problem, the ship is nose up or nose down?
Nose down.
Because?
The forward draft is shorter than the aft.
All right. So think about this. The forward draft is smaller, meaning what is the immersion level? Who's more immersed, the forward or the aft?
Oh, the other way around, my bad.
Yeah, exactly. It's the other way around. The aft is more immersed. The forward is less immersed. So we have it nose up. Okay. Yeah, this, again, this, sometimes I mess this up as well. But just think of who is riding deeper in the water. Okay. So other information, the longitudinal. Metacentric height is 104 meters. Look at this number. GM is 104 meters, which is huge. In roll, we've been talking about GM values of 1 meter, 2 meters. And now this longitudinal pitching GM is 104. So this is why we usually don't care about stability in the longitudinal direction. Okay. Center of flotation. .1 meters aft of midships. So with all of that information, we are told to determine what is the moment required to change trim by 1 centimeter. Okay, so that's not that complicated, figuring out the moment required. We have a formula for that. A bit more involved computation is find the new drafts. All right. So what do you say? How would we go about determining the moment required to change 1 centimeter? Before we do any computations, just this, can you picture this in your head? What is being asked for? So our ship might be on even keel. We're just asked for how much moment should I introduce, either clockwise or anti-clockwise, to make my ship change its trim by a given value. Not the trim angle, but the trim, okay? Trim has a unit of length. So how do we go about computing the moment required? What would you do? No ideas? Look here. Hey, you're still here, right? Yeah, there's 10 of you. Okay, so this is, if this doesn't make sense, tell me what we're being asked. No. Say something, anything. Okay, now I don't know if I'm still connected to you guys. Somebody just say yes if you're still here.
I'm still here trying to think
Oh,
about
okay.
it.
All right. So think about this. What does MCT mean? Moment needed to change trim by 1 meter. Okay. Always remember, trim is not angle. Trim is this guy. Difference between forward draft and aft draft. So we're being asked 1 meter is the required change in the drafts, the difference in the drafts. How much moment should we push down the ship, either in the clockwise rotation or in the anti-clockwise rotation, right? If you put a very heavy weight near the forward section, that would basically generate a downward force. And that causes the ship to rotate clockwise. This is what gives you more immersion and in the forward location compared to lower immersion in the aft location. Okay, and that formula represents exactly how much moment you need to change the trim by 1 meter. All right, for our question, we asked how much moment we need to change the trim by 1 centimeter. What do we do?
That would be the MCT times 0.01.
Yeah, so MCT is moment required for 1 meter change. We are asked for moment required for 1 centimeter change. So we just take this value divided by 100, and that gives us the moment. Okay, so that's a very easy computation. Let's do that. So we know MCT is delta 0 times GML divided by L. All right, delta 0 is 5,000 ton. So 5,000 times 1,000 kg per ton. This is ton times 9.81 is delta 0. What is GM? GM is 104 meter. And in the bottom, we have the length. Length was 98 meters. When you compute all of this, you'll get 52.05 mega Newton meter for 1 meter change in trim. Okay, so if we know for 1 meter, we know for 1 centimeter. 0.5205 mega Newton meter. That's our value. That's how much torque we need to either trim down or trim up by 1 centimeter. If you want to trim down, you do clockwise torque. Put something on the nose. If you want to trim up, put something in the aft. Okay, so that's the easy one. To think about the second one, what's the new drafts when a mass of something is moved? So let's we'd have a very rough sketch here. Let's say the LCF is somewhere here. Oh, LCF is given, right? It's the length is what? It's 98 meters. LCF is where? LCF is 2 meters aft, 2.1 meters aft of midships. Dashed line is my midships. Okay. So we're told that there is some mass that was already on board. We're not told the location, but that's fine. And it's moved forward to a new location. And by 30 meters. So we're told it's moved 30 meters. Compared to its initial configuration, what will this do? What will happen to our nose the forward section of the ship. Just intuitively, what should happen when we move this heavy container as shown?
The nose will go down and the stern will come up.
Yeah, the forward section will get submerged a bit more, and the aft will emerge a bit from the water. Okay, so that'll create a change in the trim value. Initially, it might have been even keel, or it might have had an initial trim, non-zero trim. But with this move, the change from this initial trim will be the way we described it. To figure out how much exactly, first we need to figure out what's the moment change. So when we move this guy from here to here, we are generating a clockwise moment. And we can compute exactly how much. It's just the weight times 30. So change in moment is $85 ton is 85 ton times 1000 kg per ton times 9.81 meter per second squared. Okay, so that's the force or the weight, and moment arm is 30 meters. So when you compute this, you'll get 25.015 mega Newton meter. All right. Now, think about how we use the answer from part A to figure out the answer for part B. What is it that we're trying to find out in B? We're trying to find the new drafts forward and aft in this situation. So we figured out what's the change in moment, but what do we do next?
Multiply that by the MCT to find the change in the trim.
Multiply this by MCT. I think we'll need to divide it, right? Because 1 meter change requires this much moment. Now we have the moment, we don't know how many meters this change causes. So we will divide the 25 by 52 mega Newton meter. And that'll give us what's the change in trim, okay? So I can't wait for all of you to be back in class. Well, I guess you'll all graduate before then. So change in moment is this much. So from part A, 1 meter change required 52.05 mega Newton meter. So how many meters change if we have for 25.015 mega Newton meter? Yeah. Okay. So change in trim is basically 25.015 divided by 52.05. You end up with 0.481 meters. All right. And this change in trim happens by the bow. Right? We said the nose will submerge deeper. So the draft level at the nose will rise and the draft at the aft will drop down. So that's what by the bow means. Okay, but we're not done yet. This is just change in trim, meaning, let me bring back an old sketch. Not this one. We've just found what is this difference between forward draft and aft draft. So what's this vertical distance here? But that's not what we want. We're asked to find what's the draft forward, what's the draft aft. We don't just care about the difference between the two. So to find those, we'll just use very simple trigonometry. To find new draft values. Okay, we will draw a sketch. So let's say this is the LCF and we have our water line like so. And when the water line is like this, that means more of the draft, more of the aft is submerged. So here we have this stern here. We have the bow here. All right. Then so that's the dashed line is what the initial water line would have looked like. And it doesn't have to be horizontal. We're just working with changes. So let's say, all right, fine, that's the initial water line. And the new water line looks like the solid blue line. Okay, and with our calculations, we figured out the difference between these 2 points. The height difference is 0.481 meter. That's the trim value, right? Now, we don't just want the trim value. We want, okay, initially the draft was here. How much did it move up by? So we call that delta T aft. The initial forward draft was here. How much did it move down by? We call this delta T4. And once we find those two values, then we just add or subtract the original given draft values. So we have here, let's call this our trim angle. And now to figure out the distance between this LCF and this guy and here, these horizontal distances between LCF and aft, LCF and 4, we can find very easily. That's depends on the data that we're given. So let me bring back sketch. LCF is here, total length is 98, LCF is 2 meters behind midships. So we know exactly what the distance from aft is. This is 98 over 2 minus 2 meters. So this is 98 over 2 minus 2.1. And the same, similarly, distance from the 4 is 98 over 2 plus 2.1. Okay. Once we have these triangles, we're basically done. It's just trigonometry from this point forward. Tan of theta is, there's several ways for us to write this. Let's look at this bigger triangle, and we can write tan of theta is 0.481 divided by the whole length, 98, right? The big triangle here. Okay. Or another way to express tan of theta is using this small triangle here, the little one here. So it's also equal to delta T4 divided by this length here, 98 over 2 plus 2.1. Okay, and when you compute all this, it comes out to be 0.251 meter. The 0.251 comes from this here. So now the only unknown here is delta T4, so we can compute that very easily. So this gives us delta T4 is I don't know how much it is. I have to, let's see. Can somebody tell me what that is? Okay. It is what? 0.251 times 98 over 2 is 49 plus 2.1. 12.82. Weird. No, something is wrong here. I think this number is, okay, let me see. 0.481. Yeah, that number is wrong. So 98. Yeah. Okay, yeah, that number was wrong. So 0.0049. Okay, perfect. Yeah, so the ratio here is 0.0049, and when you compute delta T4, you will get it's 0.251. Okay. Same way we can compute delta T aft. Okay, same exact way. So we say tan of theta is, again, big triangle, everything is known, so is 0.481 divided by 98. And also, if we use the little triangle in the back here, this is theta. So we get this is delta T aft divided by 98 over 2 minus 2.1. And when you do all of this, you will get delta T aft is 0.230 meters. Okay, that's the change in draft at the forward location and the aft location. If we know the change in draft, we just add or subtract from the original values. So original values for T aft, what was it? It was, T aft was 6.2 meter, and T forward is 5.5 meters. Okay, so T forward final and T aft final. Initial value was 5.5, 6.2. All right, you tell me, what do we do? Do we add these two changes to both of them? So should we say the final value will be initial value plus 0.251 for both the fore and the aft? That's the initial numbers. How do we get the final numbers?
We are the delta T4 and we subtract the other one for the other one.
So you're saying we take delta T4 and add it to the top, but we subtract the other one from the bottom, right?
Yes.
Yeah, and that's correct. Wait, let me see. I think it's the opposite way. Okay, so see, what has happened? Our initial water line was here. Now the water line is higher up. So we have increased the aft draft. So we will add for the aft. Okay. No. Give me 1 second. No, you're right. We moved it forward, right? Okay, okay. So
It's just the graph, but we move it to the front.
correct, yes. Did I draw the graph incorrectly? I think I drew the graph incorrectly. Yeah, it should be pointing up, right? We moved it to the front, so the water line here should be higher than the water. Well, the change in water line here should be positive. Change in water line here should be negative. Yeah, you're right. So I drew the graph, this triangle the opposite way. It should be flipped like this. Just make a note of that. Flip upside down. Yeah, so you're exactly right. Since we moved the mass to the nose should have a higher draft by exactly 0.251. And the aft is comes out of the water. So this should have a negative 0.230. So we end up with 5.75 meters and 5.97 meters. So still we are not even keel, right? There's a difference between the forward and the aft values. But that's fine. The difference is not huge. Okay. So that's how you figure out what finding the moment. First, you need to find the change in moment. Then you need to find, okay, how much does trim change by? And once you do that, you can figure out how much the drafts change by. If you're doing your senior design projects, if you have a payload you want to carry, you can do this sort of analysis and quickly figure out whether your trim would be too much or not. All right. So let's do another example. This time, let's start with a sketch. And then initial water line was something like this. And final water line looks like so. This gives us draft in the aft. And this gives us draft in the forward. All right. This is 120 meters from aft perpendicular to forward perpendicular. And then distance to LCF is given to be 64 meters. And values for TA and TA is given to be 10.62 meters. And forward is 9.84 meters. Okay, so this time I think I drew the sketch correctly. This submersion at 4 is less than submersion at aft. Okay. Then this time what we'll do is, all right, we're not writing at even keel. We have some difference in drafts. We will start loading cargo onto the ship, and we will also start unloading cargo. And we will see how these two things change, the TA and TF. We're given that TPC is 26 ton per centimeter. If you remember, we talked about this a while ago. So this is how many tons you need to add on to increase the water level by 1 centimeter, or how many tons you need to remove to decrease the water line by 1 centimeter. So this is ton, TPC is just ton per centimeter. You're also given MCTC. This is moment required to change trim by 1 centimeter. That's where this extra C comes in. This value is given to be 148 ton meter. Okay, again, look at this. In standard SI units, we would say moment is a Newton meter, but with ships, when using newtons, you immediately go into talking about mega newtons. So sometimes people just use ton meter. This is not, do not use this ton meter sort of unit anywhere else outside ship design. Okay, so for 1 centimeter, you require 148 ton meter. For 1 meter change, you'd require this times 100. Then we're also told the LCF is 64 meter forward of AP and 4 meters forward of midships. Okay. So that's the initial condition of our ship. Then we're told we load and discharge cargo. How much? We load the first container, which is 450 ton. We load it at 25 meters from AP. And we load another container, which is 320 tons, 100 meters from AP. And then we discharge, meaning unload a container, 140 ton, 110 meters from AP. Okay, and after we do all of this, the question is, what are the final drafts? So finish writing and then we'll talk about what's happening. All right, so we load on a container, we load on a second container, and unload a third container at different positions. So let's think about what is happening. We put 450 Newton, 25 meters from AP. First thing to think about, our ship will rotate about the LCF axis, okay? So this is our hinge, it'll rotate about this point. When we add a huge container 25 meters from AP, will it be a clockwise rotation or an anti-clockwise rotation? Meaning, does it try to make nose up or nose down?
Nose up.
Okay, because?
It's closer to the back.
Yeah, it says 25 meters from AP, right? So 25 meters from AP would be somewhere here. So we add a weight here. We know this is our hinge. So we're pushing the ship down, nose will rise up, okay? So this we do for all of them. The second container, some weight, 100 meters from AP. Let's see, 100 meters from AP is somewhere here. So this would cause a clockwise rotation, so nose down moment. So just to keep track of that, let's mark this. This is nose up moment. That guy is nose down moment. And the third one, we're unloading 140, 110 meters from AP. So somewhere over here again. This is nose up or nose down? The last container.
Nose up because it's unloading.
Yeah, this time we are unloading, so we are removing mass. It's like force up. So that'll cause us to rotate with nose up. So this is also nose up. Okay. Now, once we figured out our direction of rotation, clockwise or anti-clockwise, we know we can assign them plus and minus signs. So net change in moment. By the way, I will I will introduce one confusing thing here. So remember, for us, x the x direction is pointing in from aft to fore. The y direction is pointing into the paper, and the z direction is up, right? So yeah, I don't like this because this is not a right-handed coordinate. This is a left-handed coordinate system. Oh no, wait. It is still right-handed, right? X, Y, so, and Z is up. But we're very used to talking about counterclockwise rotation is positive, clockwise is negative. But in this case, our y-axis is pointing into the screen. So clockwise rotation is positive, counterclockwise is negative. Okay. So this guy is negative, this guy is positive, this guy is negative. So first thing, again, whenever we talk about what is the change in draft, what is the final draft, you should always think of, okay, we need to work with MCT. So first thing we should do is compute what is the net moment being caused by all of these things. The net change in moment. First guy is negative, minus 450 ton times what? Should I put 25? We need force times moment arm, but you could change this ton to kilogram and then to Newton, but fine, let's keep this as ton for the time being. So weight times distance. What is the distance?
$39 meters.
Because?
It's from the distance from the LCF.
Yeah, so remember, our hull will rotate about this point, the LCF point. So we need to figure out what's the perpendicular distance between the LCF and the loading position. 25 meters from AP. So 25 from AP. The distance from LCF would be 64 minus 25. So this is 64 minus 25 meter. Okay, same thing we do for the others. So we have, this is plus 320 ton times, this time 100 minus 64 meters. Then we have a negative 140 ton times 110 minus 64. Okay. And when you compute all of this, you'll end up with negative 12470 ton meter. So that's the change in moment due to this unloading and loading operation. All right. If we know change in moment, we know how to compute change in trim. So net change in trim is basically this 12,470 ton meter, and we're given MCT. What is MCT? 148 ton meter for, well, we can just say per centimeter change in trim. When you compute this, you end up with 84.3 centimeter change in trim. Or 0.843 meter. Okay, fine. That's the change in trim, but we still don't have the final drafts in the fore and aft positions. So we do the same trigonometry we did earlier. Fine, change in drafts. Let's do a sketch. This time, let me think about it before I draw it. So, a negative moment, meaning we are out of plane. So nose up means it should be slanted down. No, forward. Okay, think. So change in moment is negative, positive, negative. Nose up. Okay, nose up. Okay, so it should be slanting down. Yes. Okay. All right. So if our initial level were like this, we have a nose up motion, so we will get this. Okay, and then we know this level. You know, this total distance is what? 0.843. And this length is what? Is given? Where is it? 120. Okay, perfect. And LCF location we know. So this is LCF. This is 64 from here. And 56 from here. Okay, so again, we've just drawn our triangles and we'll use trigonometry. So tan theta is the big triangle tells us it should be 0.843 divided by 120. All right, and this small triangle tells us it's delta T4 divided by 56. And the small triangle in the back tells us is also equal to delta T aft divided by 64. So with this, we can four is all right. So once we determine change in draft, we know how to compute the final draft. So draft final and T aft 4. Okay, what was initial? 10.62, 9.84. All right. So which one's plus, which one is minus? Where do we add? Where do we subtract? This time the sketch is correct and we're nose up. So which one should increase, which one should decrease? What have I done here? Okay, this is for final. Yeah, sorry about that. So will the aft draft go up or down? Will it increase or decrease?
Aft will decrease.
The aft will decrease. Anybody disagree? I think I disagree, but somebody else disagree? Think about this. It's pitching nose up, right? When nose up, meaning the aft part is riding lower in the water. So does that make sense? Tom, why would it would increase?
I guess I'm confused on what the lines are. If the line with the theta is the change in the water line, then you would think that the bow would be going down and its draft would increase and the aft would be going up. Oh no, you're right. I got that backwards. If I think of that as the water line, okay, I got it.
Yeah, it's the water line. So the more of the hull is dry at the bow, and more of the hull is submerged at the stern. Yeah. So yeah, even I mess it up sometimes. I saw in the previous example. So this is, we do a plus for the aft. So we have a 0.45 and a minus for this guy. So we end up with okay, 457, 7, 2, 2, 1, 1, no, 0.10 meter. And then this is, oh, too many, okay. 10 minus 7, 7, okay. 13 minus 9 is 4. 4, 12 minus 8 is 4. 4, 8, no, 9. Yeah, okay, 8, 4, yes, 9, okay. Okay, so this would be the change in, well, the new aft and forward drafts. If the only thing that were happening was rotation. But in this problem, there is one more thing that happens. Remember, we are not just moving weights from one point to another. We're adding and subtracting weight. Okay. So think about what happens to the hull. The hull in total will either rise up or it'll submerge a bit more. So we need to account for that as well. Okay. So the new drafts due to rotation, we've figured out what the change is. But due to mass loading and unloading, we have to add or subtract a constant value. So to do that, we have a change in total mass. Due to loading and unloading. What this means is the entire hull will either rise or sink. And we can figure out exactly how much. Exactly how much is can be calculated using TPC, tons per centimeter. If we know we added an extra 26 tons, my whole hull will sink down 1 centimeter. Okay, so we will use that value. So change in total mass is so we added a 450 ton, we added a 320 ton, and we subtracted a 140 ton. So in total, we have added 630 ton. Okay. So with this, we expect our hull will ride lower in the water, meaning the total draft will increase very slightly. So this gives us sinkage is 630 ton divided by, what was it, 26? Yeah, 26 ton per centimeter. Okay, and this gives us is 24.2 centimeter to 0.242 meter. Okay. So what do we take? We take this number 0.242 and what do we do? Where do we add? Where do we subtract?
Wouldn't you just add to both?
Yeah, we add the same number to both aft and fore because the whole hull is sinking by 24 centimeters. So, which implies we get T aft is 10.07 meter plus 0.242. Did I do this? I think it should be 11. Yeah, so it should be 11. Sorry, this is 11, not 10. 11.07 meters plus that. Okay, so we have 11.312 meters. Okay, and T4.447 plus 0.242. 8.9448, 426, 9 point this much meter. So in the end, with all the unloading and loading, those are the drafts we will get at the two positions. Okay. So remember, whenever you try to compute trim changes, think about both phenomena. First, whether the hull sinks or rises and how much it rotates. Okay, when we combine the two, we get the total drafts. And again, be careful about noses going up or down. It just takes like half a minute of thinking, and then all your signs are correct. All right. Any questions?
Yeah, I have one. So that graph you drew is the water line, right? So you assume that in that visual at least, the ship would stay in the same orientation, your water line's just shifting. For the graph at least.
Yeah, exactly. So it is just to make our life easy. The hull on paper remains the same, the water line shifting. But in reality, the water line remains horizontal and the ship would be nose down or up.
Okay, perfect. Thank you.
Any other questions? All right. Okay, so at this point, we've basically covered all the basics of figuring out stability and the state of your ship. You know how to compute you know how to compute if you have an irregular hull, how to compute the displacement. You know how to compute the heel angle, the trim angle. All right. And now all of this we have done for an undamaged ship. We'll start, and also for small angles. We'll start talking about what happens at very large angles of roll or heel or trim changes. And we'll also think about, since we are ship designers, we have to think about what happens if there's damage to the ship, okay? How do I make sure that it still stays stable, it still stays afloat? So we'll look at what happens if you run aground, how that changes the stability status of the ship. If you poke a hole in the hull and starts filling with water, how does that change the stability characteristics? Okay, so that's the next part of stability we'll talk about. And once we finish with that, we'll talk about, start talking about dynamics. So what happens when the ship moves? It generates waves, how it dissipates energy, how we can design small experiments in a water tunnel to characterize what happens to a full-size ship, et cetera, et cetera. So, and the next small topic we can talk about is stability. So this is a topic change. We're done with trim. Stability at large angles. Stability at large angles, it's not as straightforward to compute things. So we usually rely on the charts provided by the person who designed the ship, who computed all of this and plotted it on a graph. So we have considered stability for small angle changes. Previously. Okay, and for small angle changes, what we did was we computed the GM, okay? And if it was positive, we said, all right, this is stable. And with small angles, M did not move. That was one of the big assumptions. The M location doesn't change a lot for small angles. Okay. But that's not true for large angles anymore. So for large angles, M is no longer static. And since M keeps moving around, GM is not a very good measure of stability anymore. So in this case, GZ is a better metric. I'll tell you what exactly GZ means. It's basically the moment arm that restores is the restoring moment arm. So GZ is a better metric to measure stability. This guy is the moment arm. Or the writing arm. Okay. So let me draw two sets of sketches here. this on the right, we'll have 4 large angles. And on the left, we have 4 small angles. Okay, so generic hull here. That is healing. And waterline. Okay, and then this scenario, we know, we talked about, we have buoyant force up here. And let me mark this Z, that point is Z. And we have buoyant force acting up there, and we have weight acting downward here. Okay. So this we already know, and we know the moment arm is GZ here. For larger angles, again, we have something similar. Okay, yeah, actually, there's a lot of stuff to mark here, so let's finish that next class. We'll have quiz, I guess next Friday would be a good time. So let's have a quiz, short quiz next Friday. I'll send out an announcement. And I'll tell you which homework to focus on. Any questions? All right, so again, get started on your project early. If you have trouble finding team members, email me and I can like send out a blast email that so-and-so is looking for teammates.
What will be the quiz on?
I'll in the announcement, I'll tell you which
Okay.
topics.
All right.
Yeah.
Thank you.
Okay. All right, see you guys next week. Don't forget about your homework, the latest homework.